Hello and welcome to a Building Smart webinar. This webinar is part of the Building Smart Virtual Summit for Spring 2022. Thank you for joining us today. My name is John Proctor and I am your moderator. Details of today's webinar are on the screen. This is the Infrastructure Room second session, Part A. Part B is tomorrow morning, and we will be hearing about IFC Tunnel. We will start with project lead Michelle Reeves, who will give a general update on the IFC Tunnel project, and then we will conduct the first expert panel with Andre Bormann, Lars Wikström, Jan Christian Torren, Heiko Eisbacher, and Jonas Viel. So this webinar is scheduled to last for 2 hours, when we will have a short question and answer session at the end. The webinar has been recorded and will be made available in the replay section of the event within the next 24 hours. Before I hand over to Michelle, I'd like to remind you that your phone lines will remain muted for the duration of the webinar. If you have any questions or wish to make comments, please use the comments box in the control panel on the right-hand side of your screen. So any questions or comments, please use the comments box. I'd also like to bring to your attention the information that is on the screen now. Building Smart is committed to ensuring that participation in the development of standards is unrestricted and the process for their adoption is transparent. And standards that are developed do not favour any particular provider, but are open, non-binding and accessible to all. Please take note of our antitrust code of conduct. Now I'm going to hand over to Michelle.
Okay, thank you. Hello, everybody, and thanks for joining us today, specifically to those who are listening to us from Asia Pacific or Australia, where it may be really late, and those from the US or the Americas, where it could be really early. We have a very busy agenda for you today with this first expert panel, and as John mentioned, a second one to take place tomorrow. 10 a.m. CEST time. That's GMT +2. Trust me, it's going to be very informative. It's packed, but we have a lot to report to you with our consolidated conceptual model for the 3 disciplines that this project embeds. And to start with, Andrea and I will be giving you a global project update. And after this, so like in 20 minutes or so, we'll hand over to the 3 domain teams, being geotechnics, structural design, and systems. We would be taking you through the requirements that they expressed, the taxonomies that they produced, and the implementation that they've done that is leading to the conceptual model that we have today to present to you. First thing I'd like to stress is that we are basing our work on the 4.3 release, which, as you would recall, has been made public this past summer, 2021. And we are providing an extension into a 4.4 release. And of course, we benefit from all this work that has been done to cover roadways, railways, bridges, and maritime works that sit on top of 4.1, the IFC alignment initiative. And the beauty of this is that at the end, we go to get a one unified schema, which, for example, if you are, as an engineer making an analysis of the interconnection in between a tunnel and a station, for example, you would extract from this one single schema everything you need from what describes the station, the building, what describes the tunnel itself, and what describes the systems that go through those structures. So it's really one unified schema. I wanted to stress this. And of course, once this is published on behalf of Building Smart International, it is passed over through the ISO submission process. And then adds to the ISO 16739 as you would record is existing. We have a terrific team, more than 45 people coming from all over the world. And these experts are either representative of infrastructure owners, geotechnicians, bureau civil engineers, systems engineers, national prescriptive associations or agencies, and research bodies, including many technical universities like the University of Bochum, University of Munich, University of Florida, University of Leuven in Austria, and University of Sao Paulo in Brazil, for example. And I'm happy to report the addition to our team of the Portuguese Tunneling Association, who members are acting in Portugal, but acting as well very much so internationally. I wanted to stress as well the cooperation we've started with the Federal Highway Administration in the US. And this is very interesting because it is along the lines of what the AASHTO team has done with its recommendation for IFC in the US as part of the tenders deliverables. I did a quick math to assess the amount of work that we put together into this project, and I think we are close to 1.2 million of billable hours altogether. That gives you a sense of the effort that we've put into this. We've assess our scope on the basis of use cases, and those use cases cover where exchanges of information happen, both in terms of describing the subsoil or the lack of understanding of the subsoil, lack of knowledge of the subsoil, the design phases themselves, the sequencing of operation, the issue of tenders, the construction processes themselves and their monitoring, and the handover to assets management. So these are the basis upon which we define our scope for the three disciplines that I mentioned earlier. The first thing, of course, that came to mind was to define the different spaces into which we have to organize the project. And these spaces may result from the extraction process, excavation process itself, or they may be planned as reservations for the different systems that have to be installed in order to operate the underground structure. As I said, we have compiled the requirements of three disciplines. So all in all, you could say this is in fact three projects that we run in parallel. But I would add that there is another fourth project that we run, and that is the coordination in between those three disciplines. Because what this project is very much about is to facilitate, to ease the exchange of information in between technicians, civil engineers, and system engineers. And that has proven to be difficult so far. So we really have tried to understand the expectations and the constraints of the different disciplines so that each other understand well why is that important to provide that information. As far as geotechnics, I won't go into detail, Sienna's covering this, but basically understand that we have a consensus on organizing data in between factual data, interpreted models, and everything that relates to helping with the design of the underground structure in the context of a soil structure set of efforts. Next to this, we've considered as well existing standards that either the OGC or other organizations have produced over the years and are being used. So we need to make a link to these. As far as the structural design itself is concerned, we clearly decided to cover everything that is related to excavation down through TBM, so tunnel boring machine, or through more traditional drill and blast methods, and things that cover as well the so-called cut and cover structures. So this is the scope for the structural aspect of things, both in terms of what is built and in terms of how it is built, construction methods. As far as the systems that equip those tunnels are concerned, you have them listed here, and Heiko will be covering that later on. Everything that relates to ventilation, drainage, dewatering, fire protection, power provision, and safety and evacuation. So that's the global scope of our project. As a consequence of the requirements expressed there, we needed to provide a few extensions as well in terms of the geometries. André will cover that. And basically, we wanted to make sure to describe properly the transition, non-linear transition in between cross sections, something that is required for tunnels, but is required as well for bridges. So we are serving the bridge team here, the Building Smart bridge team here too, as well as those 3D grids, so-called voxels, which help at describing a situation whereby the subsoil, for example, doesn't have a well-defined continuous limits to a particular characteristic. So the characteristics there are described through values that are embedded in the cells that make up the 3D grid in question. And that's a very neat way to describe things that are uncertain to some degree. And that serves, of course, the underground structures like tunnels, but it serves as well foundations, deep foundations like for bridges, and of course deep foundations for buildings as well. So this is a rather broad impact that this and positive impact that this has, of course, on the different disciplines. And last but not least, this idea of linking external data is something that is existing today to some extent in the IFC, but we want to extend it to make it more efficient. So that's another addition. When we put those requirements together, we ran a series of national I should say consistency checks, in the sense, with national industry association, national tunneling associations, and we ran this in 10 countries, and we got over 200 comments or suggestions. So we have enough food for a second iteration of our project, whereby we will be extending the scope that we have right now. But that's for later on. As far as the deliverables are concerned, very happy to report, of course, and this is the main topic for today and tomorrow, report upon the conceptual model for the 3 disciplines in question that we have just polished. We had the first version by December, but we now have a consolidated version. And this is what the domain team and Lars will be taking you through. Of course, this is very consistent, but it's important to know what we have now in this conceptual model. It's been developed in UML through the Enterprise Architect platform. So this is available, and again covers all the geotechnical situations, the uncertainties that are associated with it, the mechanized drilling and blast excavation processes, the support and the lining techniques that are used, and the different systems that equip. So all this is part of this conceptual model. And of course, the extensions that I was referring to, but altogether, we've tried to leverage as much as possible from what was existing in IFC 4.3, and came up with a certain number of extensions that will be part of 4.4. Did a little math to compare the number of domain concepts that each of our 3 disciplines have produced compared to the railway project, for example, which was a rather large project. And you can see that this is somehow equivalent in importance. Again, just to size the amount of work that is behind this project. So once this conceptual model is ready and will be presented to you, we will be then concentrating on producing everything that software developers need, like the express schema, things that can help with preparing the translation, automate the input to the BSI, BSDD. This is mainly services platform to link classifications with a conceptual model, and prepare the different exchange mechanism on top of the so-called alignment-based reference view, MVD. We have as well in a formal approval process within Building Smart International, and that has, in a sense, already started, because we have had a series of technical discussions with the SCTE committee, which is making technical recommendations for us to improve our model, and we've taken their pieces of advice in consideration, and have integrated their wishes. So I think we are in good shape now. And the last bit will be around preparing test instructions, data sets to help with the certification process, and of course work with the software developers by providing the data that is needed, real-world project data that is needed for ensuring unit tests and storylines, a bit like the railway and the roadway team have done in the past. With that, I think I should hand over to André, and just remind you that after André, you'll have this sequence presentation, geotechnics, excavations, and systems, and we can refer to the expert panel tomorrow, which will be dealing on more the geometrical aspects of things. So André, over to you.
Okay, so hello everyone, also from my side. My name is André Baumann. I'm at the Technical University of Munich, a professor, and at the same time I have the pleasure to act as the technical lead here in the IFC Tunnel project. Let me first of all give you an overview on the process of IFC extension developments. So we typically have two different groups, and we also have them here in the IFC Tunnel project. On the one hand side, we have the domain experts. On the other hand side, we have the IFC experts, and they work closely together. So typically, we start with capturing the domain requirements in a requirements analysis report. This is what has been done here as well. And then we define more precisely the data requirements. And this is still the task of the domain experts, typically represented as a taxonomy, an extensive taxonomy. This is then the input for the conceptual model that is being designed. As we said, we use Enterprise Architect for that. And then we, on the basis of this conceptual model, we define the actual schema extensions wherever that is necessary. We first define a draft. This is then validated with demo implementations. And then finally, we have the final IFC extension, which then goes for formal approval to the BSI bodies. Let's have a closer look on the individual steps. So Michel highlighted this already. We started with an extensive requirements analysis report that was published in July 2020 with around 170 pages, where we documented in detail the use cases, the processes in tunnel design and construction, the associated data exchange scenarios, and then we came up with a number of chapters highlighting specific aspects like, for example, georeferencing, additional geometry, the role of alignment, but also then we had a very detailed description of specific items in the different domains, and our domains are geotechnics, systems, and excavation structures and lining. And this was then the basis for our domain expert groups to continue their work. And well, they came up with comprehensive and structured compilations of the object types in the domains and their specific properties. So we see these Excel sheets that have been produced, which were really helpful, and a lot of work went into them. During this process, of course, international standards, national classification, and object catalogs have been considered. I just mentioned mine from France here, and now from Germany, that have already created properties and object types. So now having a look on this from a more technical point of view, we use these taxonomies and the requirements analysis report to come up with an UML model using Enterprise Architect. We make use of the UML modeling guidelines that have been developed in the infra room and also been used in the railway room. From this Enterprise Architect model, we can produce UML reports that have been created already and handed over to SCTE, for example, for review. But we can also create XMI and use this export to use it as input for IFC-Doc. And IFC-Doc is the tool that we use to define the extensions of IFC. Everything we do there is hosted on GitHub, so everyone can see it. Everyone can raise issues, provide comments, and so From IFC-doc, then the Express Schema extension is created, the HTML documentation is created, and of course we will do this several times because typically we are not done in only one iteration, but we need several iterations of that. So we are now already quite advanced with respect to the conceptual model. So I would say it's around 90% complete. The conceptual model is based on UML, Unified Modeling Language, which is the standardized graphical notation for object-oriented data models. And we use it roughly in the way that, first of all, we directly model all the domain entities in UML and mark them as so-called virtual entities. And then we decide to map these new entities either on existing IFC entities, or at some places we also decide to create new elements. Of course, we have to be very careful because we don't want to grow the IFC schema endlessly, but still here and there we needed new entities. As I said, the conceptual model is 90% complete. So what we have done already is to model geometry and spatial structure, geotechnics, the structures and the systems. Here and there, a few elements are missing, but that's really something that can be completed very soon. And the idea is really to finalize the work on the conceptual model within the next days or the next weeks. So we have around 25 new entities, 50 predefined types newly defined, and around 250 properties that have been captured. So as I said, the conceptual model is now the basis to do the next step, to do the actual extension of the schema. And well, we use GitHub quite intensively, the BSI InfraRoom repository, where you can follow all our work there. We use this to discuss with other experts like the BSI bodies, the international community, but also to exchange with experts in the expert panels. So you can use these links that are listed here to directly access the repository. Yeah, so what is the schedule for the overall project? We started in 2019. Then in summer 2020, we delivered the requirements analysis report, which was really a lot of work here to compile all these requirements. Then both the domain groups, but also the IFC experts started to do the conceptual model development. We had the very first alpha version at the end of last year, and we will, as I said, deliver the final version of the conceptual model very, very soon. So now we started already with the schema development. We will continue to do so until I would say summer, early autumn this year, and then would have a first candidate standard for IFC 4.4, which will then include the extensions for IFC tunnel. And then, well, we probably will have a deployment project where we help and support vendors in implementing these new data structures and yeah, give them support for that. All right, that's it from my side, and I now hand over to Lars, I guess.
I think you hand over to me.
Sorry. I'm sorry.
Indeed. Please go ahead.
Yes. So I'm Jonas Weil, and I will do this part of the presentation together with Lars. But I will start with the introduction from the geotechnic perspective, let's say, to give you a bit of a background before we look at the conceptual model for that part. So I will give you a brief overview, if I can jump over. Yes, on our background and motivation from, let's say, from the tunnel domain. Of course, tunneling requires a detailed description of the ground conditions. That's a clear fact. And the typical challenge for large infrastructures, such as tunnels, are, of course, large volumes of geological, geotechnical, factual data that we collect and need to organize. We need to translate all these facts and these findings about the ground conditions and the geology into simplified models for geotechnical purposes, but of course they must be representative and they must work for different purposes. So there's many different use cases for geotechnical models that we need to cover. Then we usually deal with very long project lifetimes, can be decades. During this time, we collect more and more knowledge, we get more and more additional data, and we need to update our models frequently. Our models are quite different to building models due to the fact that we deal with high uncertainty. So we start with very little knowledge about the ground because we don't have much insight and not much site investigation. And during the project lifetime, we develop more and more sophisticated predictions until we reach construction stage where we finally find what is actually there. So during that time, we gain even more facts, even more documentation, information that we need to bring into the model and compare it to the prediction. Why is this so important? Of course, the ground conditions, due to this uncertainty, are a major factor of uncertainty for the whole project regarding costs and project time. So for this reason, we need efficient ways to deal with all these challenges. We heard a good introduction about the IFC Tunnel project and our activities. From my side, just a bit more focus on our tasks. The requirement analysis report that Andre just mentioned included detailed description of use cases we are going to support. We almost finalized the conceptual model, as Andre just said. This STEAMA extension or our work also includes some concepts to deal with uncertainty. As I said, that's a very important fact for us. Regarding geometrical representation, something quite new for IFC will be the Vox models. We're going to talk about that. And for us, a major challenge or requirement is to define a good link from a model of the ground conditions to the design. And I will show you the concepts that we have for this in my following slides. Regarding the input, some brief overview. Maybe you saw this in previous summits, previous presentations. We collected input from many existing standards, and one very important source for us was the standards by OGC. There's still a back and forth with this. So this is something from the requirement analysis report where we described what was already covered and where we see a need to extend data schema. Did the same analysis for the existing schema extension from 4x3 for the techniques, where we still see some gaps that we would like to have filled for tunneling applications. Regarding OGC, I briefly like to mention this initiative, this Geotech IE initiative. If you get the slides, we'll also have a link to the project. Important fact from our side is that we actually provide the conceptual model that you will see now as an input to this project. So this will be discussed in an even bigger group, very established representatives for established standards and domain groups, and a common conceptual model with OGC in the future is a big goal. That we don't want to reinvent the wheel and to keep the standards aligned. Let's come to our work. This slide has been presented before. You might be familiar with these use case descriptions that have been published in 2020 with the requirement analysis report. To repeat it quickly, we focus a bit on geofactual data. I will explain later why this is so important to you. And then we have several use cases throughout the lifetime of a tunneling project. I would like to summarize this with some examples in the following slides. Very important for me is now to show the focus. Based on this use case descriptions, what do we think are the essential needs for the STEAMA extension? Very important is the support of factual data. Factual data for us are any observations and measurements regarding geology and geotechnics. So it can be lab test results, it can be borehole data, it can be any other kind of test results that are collected, it can be field mapping, anything where we have confirmed knowledge that we need to localize in our model and that we need for further assessment. And why do we think that IFC would be a good option to produce or to exchange these data? We think there's no existing established standard that carries both the geometry and the semantic model and properties to these observations or to these geometrical objects. So we think having IFC as a tool for this would be very helpful for importing the data for further interpretation and also use the existing software for visualization. So we need a base for spatial assessments and visualizing this data that we can continue working with it. And of course, we always need to show where is the confirmed information. The next step is for us the interpretation. So what we also need to have supported, we start in tunneling from the very beginning. The ground is so important for us that that a fundamental understanding of the geology is of high priority for us. That's why we want to have geological models that have been developed already, for example, by geological surveys or by other projects. We need to start from there and have this in our work environment. So geological models as a basis for our engineering judgment are one point. And then we need to reclassify the same ground. We need to fill the same volume in our mountain, in our project area, with a different classification for geotechnical purposes. So we need geotechnical models that classify the ground according to our requirements from the design perspective. And this brings us to the last point. When we have gathered all this knowledge and this good description of the ground conditions, we need to link it somehow to the building model. And for this, we have a quite good concept, as I think, that I would like to show you in the next slides. Starting with this overview. So, as we just heard, factual data are most important for us. They show us existing knowledge. This can be geophysical surveys, boreholes, test results from different sources, in situ testing, lab testing. It's field mapping data and a lot of existing literature maps and so on. All of this is compiled to form our interpreted models that fill our model space, for example, along a tunnel corridor. We see here geological units. We see major fault zones that have been modeled along this alignment. So these models describe the ground where our project is located. But in the next step, we need to relate this to the design itself. So we see here an example. The classical approach to this is a longitudinal section. That is what is commonly produced by geologists in a tunneling project. Once the alignment is fixed, or once there is at least one alternative for the alignment, the geologist would draw a longitudinal section and describe the major features that are relevant from his perspective. Maybe fault zone, maybe contacts between different layers, and so on. What you usually include in such a prognosis longitudinal section is a band. It's a line below the drawing that indicates you the key properties along a certain part of the alignment. And we are going to adopt this approach in a BIM model. So we say we can split the alignment in certain intervals based on the expected geological, geotechnical conditions. And then we can supplement this part of the alignment with attributes that describe these key factors, these key aspects that are relevant for design at especially this part of the alignment. This is for us the input to the designer. And it's also a measure to deal with uncertainty, because in tunnels with high overburden, for example, we can have a lot of drill holes, but we can never tell in detail where exactly do we expect a certain fault zone, which thickness exactly will it have here, maybe 2 or 3. There's always an uncertainty remaining. And a common way to deal with this is to work with predictions and longer intervals to say we have an interval number 1, and here we expect certain ground types, but we cannot tell exactly where they are. We cannot have a geometrical model of each and every layer, but we can tell you have like 70% of this material and 30 of this. We can describe the discontinuity settings with properties. Based, of course, everything based on the assessment. We have an existing model, and we can define these limits, and we can define the values for the properties based on a model. So we can fill a prediction model for certain parts of the alignment, and the designer can work with this. So based on this design-related prognosis, the designer can have a prognosis design model to say, for these conditions as described here, I will need the following excavation methods. I will need the following support types. I might need some special measures like injections to deal with the groundwater, certain health and safety measures depending on, let's say, asbestos minerals, whatsoever. There might be gas occurrences somewhere, and this can be described efficiently with such a model of zones along the alignment. And the designer can have a corresponding model that can be used for a cost estimate, that can be used for any permit, and that can be cross-checked against the encountered conditions. That's the next point for us. Once the project has started, we collect a lot of information. Usually you have geologic documentation during construction. So everything you predicted will be checked now. For every round you blast in a conventional tunnel without TBM, you might document discontinuities, you might document groundwater inflow, and you might document the distribution of certain materials in the tunnel phase. This can be now checked model-based against your prediction model. And you can easily compare expectations versus encountered conditions. Of course, the same applies for the design. So based on these conditions, certain support types are installed, certain measures are executed, and the design model develops along, the as-built design model develops along with the as-encountered geology model, let's say. So this is a bit describing a workflow that we have in mind. And this brings us now to the requirements to the model schema or to the conceptual model. This model is in generally subdivided in 2 parts. We distinguish factual data described in Book A, that's our working term. So everything that is measured or observed and included in the model belongs here. And then we have Book B with interpreted models with layers in between these points of observation. And then, as we just saw, this Book B and the essence from Book A and B can be linked to Book C, which includes the design solution, and is also that's the place where risk assessments and things take care, because they are related to the building already. So that's our starting point. And I briefly list the key elements that we expect for these Book A and B before I hand over to Lars, who shows you how this looks in the conceptual model. So for Book A, we started with a collection of domain-specific typical types of data. Typical information we receive in a tunneling project have been subdivided in classes and are covered now. This includes objects that will need to be related to a certain geometry, and others that are just semantic elements, like, for example, a test results. We can have many test results that are related to one sample, and the sample might have the location, but the test results have to be linked to it. One important point for us is that we are dealing partly with very extensive data sets, partly with well-established comprehensive standards for exchanging this information. And we need an option to link external data sets. This applies especially for very big data sets, like very detailed logging data with geophysical methods, or machine records from drilling rigs or drilling jumbos in tunneling. ball data. So we don't want to bring all information that is there into IFC, but we also need a chance to link external things. The second similar point is that there is a lot of existing standards describing test methods and describing the way results are being prepared. And of course, we cannot reinvent all this. And of course, IFC schema cannot cover all these properties. So an important point for us will be custom property sets to cover such existing standards for test results. For Book B, most important, as I mentioned before, is that we can classify the ground according to different systems. So we can describe the same stuff, the same material underground with different classifications depending on the purpose. So we might have a geological model that describes the age of a formation. And then we have a certain geotechnical model that tells you how this material can be excavated efficiently. And you might need another classification to tell you what is relevant for stability analysis, what is relevant for ground improvement, and so on. So depending on the geotechnical question, we need the option to have alternative classifications. We will have overlapping models describing the same part of the Earth. And the new thing that I just showed before is what we call the geotech synthesis model. This is the design-related prognosis model that I just showed that should link everything described by the other models to the building or with reference to the alignment. And the last but very important point for us is that we also need to include a mechanism how observations are linked to interpretations. So if we have a model of certain layers, let's say, interpreted materials, we need to describe how we derive the geotechnical parameters that are assigned to this layer. And we need a link that actually works in both directions. On one hand, it's efficient to label observations to say this test here or this result was used to define properties for this layer. On the other hand, it's good to have information attached to the layer, let's say, which factual data have been used to define characteristic parameters that are used for further analysis. So that's something we are working on to use existing functions in IFC to establish that link. And from here, I would like to hand over to Lars, jumping to the next slide. Lars, just let me know when I should change the slides.
Yep, thank you, Jonas. Yeah, my name is Lars Wikström, and I've been working in the IsoTunnel project with a conceptual model together with the rest of the technical team and the domain experts in the different domain groups. There will be a lot of slides looking kind of similar. So I have first a short introduction to how this works, and maybe I'll have to skip over some slides due to time restrictions, but you can then look at this in the reports yourselves. The UML model, as has been explained, it captures the domain requirements, the taxonomies presented by the domain teams, and expressed in the form of UML. And the first thing is that with some model, so you have some order in this. So for example, for geotechnics, we have then for the domain taxonomy, we divided this into Book A and Book B, and inside Book A and Book B, you have sub packages. And as you see here, you have in Book A, you have observations and measurement results. You have spatial geo-obs elements, which are sort of containers for these observations, and you have tests. And for Book B, you have interpreted objects, and you have also, similarly, you have containers for these interpreted objects. So we can take the next slide. And you can click a couple of times, Jonas, there is, I think, some animations here. So this is just to give you an impression on how to read these UML diagrams. As Andre mentioned, you have the domain concepts and the taxonomy you have modeled as virtual entities in UML. So you know what is coming from the domain and what is sort of IC specific. And of course have structure, like you have an IFC entity which we just reuse as it is, and if you have that red border around it, it's something that we actually proposed as new, and if it's this sort of brownish yellowish border, it's something that we would like to modify in some sense. So that's sort of a crash course into how to read the UML diagram. So we take the next slide. Yeah, so sorry, this is very, very small, I see now. So from book A, you have certain containers then that sort of carry then the information, for example, about observations. And in there you have, for example, boreholes. IFC borehole is something that exists already in IFC 4.3, but we sort of introduce maybe a slightly wider meaning, since it now can be sort of the carrier of these observations. And then we have sensors as one option. We have, it's actually so small so I can't see it. Yeah, and we have, maybe I can do something here so I actually see it myself.
I can read it loud. We have borehole here.
Yeah.
We have sample here.
Yeah.
We have sensor with a reference to the existing
IFC sensor
concept. Yeah.
Yeah.
Then we have mapped zone and tested zone. These are the two new features with some predefined types.
Yes, and there we actually then propose to use IFC spatial zone and a new predefined type for that we just call observed zone. So we actually collect all these mapped and tested zones into one concept in IFC. And to the right there, I put just something showing from the requirements analysis, showing one way of representing data for a kind of mapped zone. In this case, it's actually the tunnel face. And this might be looked at a little bit closer when it comes to the actual representation of it, because there are different ways of representing this kind of data. But that tunnel phase is one kind. I don't know if you want to add something, Jonas, there. But...
Yeah, we will have an example on this. So in some of the next slide. Yeah.
Yeah. So let's continue then to the next slide.
There was one thing I was trying to add here for the borehole. We just mentioned that before. For borehole, we might have very extensive data sets that we cannot push all into the IFC file as we agreed. So we are going to support 3 options. That is the idea. We can have a very simple representation in the model, like just a shape of the whole borehole and reference to external files. But we can, of course, distinguish observations on the borehole. This could be interval representations. And these can either use property set defined in the IFC schema, a very simple one for general logging data. But we are also eager to link this to more sophisticated existing ways to transport logging data and use it to link existing files like AGS files or any other file that describes these observations along a borehole for a certain interval or a certain point. Because we know there's so much existing standards and that can be very extensive data sets that we are eager to have this option supported, let's say. And then I jump on. Mm-hmm.
So quite small again, but anyway, in there we have then the observations, and first of all, on top there we have two sort of main types. We have a borehole data representation subdivided into more specific classes like borehole construction, geolog intervals, and different things. And then you have observed objects. And in this case, there will be a slide later then showing what we have actually done with the observations. But the observed objects we have actually selected to introduce a whole new concept in IFC, which is then an observation. And these different types of observed objects are then defined as predefined types for that entity. And regarding the borehole data representations, we have then the IFC borehole as an object, and our proposal is then to use, like Jonas showed in the previous slide, either predefined p-sets or external data to represent this kind of information connected then to the borehole in that case. Mm-hmm. So I assume we can go to the next slide. Yeah, so here we actually come to the observations and the modeling of that in IFC that we propose. We actually propose to introduce a new entity under IFC product, actually, which we have called IFC product data. And there is already predefined relationships or associations in IFC, rel assigns to product, which we can use then to associate product data to any other product, such as sensor or borehole or these observed zones, for example. So you could attach observations to all of those. And we actually then introduce a generic IFC observation. We thought that it could be a good idea to be able to have also other kinds of observations, not only for geology and geotechnics, but specifically for geology and geotechnics, we have this geoscience observation entity that we propose to introduce. And for that, we then define a couple of predefined types capturing the requirements from the domain here, the different types of observations that you can actually then define and use in IFC. And of course, as any other object, these observations can carry information such as property sets or external data, again, if you like. So, yeah. So I guess we can skip to the next slide.
That's the next one that's linking to an example. So I would like to very briefly show how we, from the domain side, what we have in mind to do with it. So we heard that we have this spatial observational elements, for example, a mapped zone. A mapped zone is for us any location or any place where we make this observation. This can be the tunnel phase during execution of a project, but it can also be a field outcrop, it can be a cut slope, or it can be a trial pit where the geologist goes and makes mappings and logs discontinuities. So we see here example of this observational elements, the place where we make the observations, and then we link these predefined types of observations to it. And this can look like this. The tunnel phase is the mapped zone, as we call it. On this, we have mapped units. That means we have a patch where we observe a certain material. That's a mapped unit here and another one here. And we might also have discontinuities that have been traced somewhere, that have been measured with a compass. We have water inflow points that have been documented in the tunnel, and so on. So these are types of observations that are attached to a certain place where we make the observation. And this can be, of course, as I said, not just be a tunnel phase, but any kind of outcrop where the geologists make these observations. And from here we move to the tests, Lars.
Yeah, and tests, you don't have to maybe, like me, read all the details here, but there are a lot of different tests specified. And in this case, we have actually then defined also the test as a kind of observation, and we have sort of generalized this into actually now 3 predefined types, and that is in situ test, geophysical survey, or lab test. And the rest of the details, when you go further down into the structure for tests, we consider those like p-sets, as you see on the right there. And you could also have external data, which we can see on the next slide what we did with that. Again, sorry about the small text here, but what this is trying to convey, if you go back, there is already an existing structure in IFC where you can reference external documents, but documents to most people, they are sort of possible to render by a machine, but they are sort of meant to be understood by humans. So we actually add a parallel structure there, or propose to add, where we also can reference external data sets, sort of using the same mechanism as is already in place in IFC. So, and actually we propose to reuse the same structure for metadata, for example, if you would like to have that as well. And I think this will be also presented a little bit more tomorrow. Yeah, so I think we can skip further.
Now we come to book B.
Yeah. And this is also me, right?
Yes, that's
so book B, we have sort of a similar structure. We have these what we can call containers, in this case models, and these containers can then contain interpreted objects. So I guess you will have to read, Jonas.
yeah. Maybe I can elaborate this a little bit.
Yeah.
So this relates to the different classification of the ground that I mentioned. One of the containers would be a geology model, and inside of this in this container we would have this geoscience objects, or geoscience, how do we call them? Geoscience features, I think. So this could be, for example, a fault, a contact, anything that is modeled inside the geology model, or it could be a geotechnical unit, a discrete discontinuity that has certain geotechnical parameters, like a shear strength that is included in the geotech model container, or a groundwater table, or a permeability related aquifer model, like a hydrogeological unit. So these are these geoscience elements, and these are the containers.
Yeah,
I think the next slide lists these geoscience elements again.
Yes, so it's the full. So there we actually introduce then what we call a geoscience feature. So the container we have called an IFC geoscience model, and these then things that you can put into these models are we call IFC geoscience feature, and it's actually one extra IFC entity with a couple of predefined types, sort of in a similar structure as the rest of IFC then. Yeah.
I think from here we have another overview.
Yeah, so this just shows sort of, this is like a compilation of the things that we have actually added on a high level. So we have IFC product data that we added, I talked about that, or with observations, and also voxel data that will be elaborated tomorrow. And for observations, we add then geoscience observation. And then on the other side, we have these geoscience models and geoscience features for the interpreted data. So that's sort of a simple picture showing the sort of essential extensions then to IFC that we propose.
Mm-hmm.
Yeah.
I think, I'm not sure about the order, but we're getting back now to the
Yeah, so I think we can skip this. This is just
Yeah.
again, this shows this was just a sort of compilation of the things that we have added
that are new.
that are new in IFC.
Yeah.
Yeah.
I think the slides will be shared anyway, huh? So
Yeah.
that people can look at it in detail.
Yeah, and I think we are sort of done.
Yes, we're done. At this point, I would just, because that's from our perspective, from the domain people, something most important, that we have the geotechnical unit. So this would be one of these geoscience elements that relates to a geoscience model, to the geotechnical model. So this is something that classifies the ground in certain materials. And here we have several p-sets depending on the material. If we're talking about soil, or if we're talking about rock that is controlled by discontinuities, or that we say we cannot tell in detail where the strength is, in which, how high the strength is in a certain part, we might just give you an envelope and say, in this part, we have these kind of materials. So this is just a quick overview to show what we are going to do with these elements. So we are going to support with this geotechnical unit several concepts to distinguish the ground material. We can either do it in detail and say we model every layer with a geometry, and the properties of layer B include, for example, compressive strength, shear strength, stiffness parameters. Or we don't do it and say we just model this part, this green part, and say here in general we have these materials, and the rest can be found in the geotechnical report or in external documents. So we want to give the modeler the freedom to have all these options, but to deal with the uncertainty we have, and to deal with the difference of knowledge that we have for certain parts of the project. And uncertainty is the last slide, actually. This is just an outlook. We cannot tell in detail, but we are really working on a typology to say which are the types of uncertainty that we have in the model. And we are working on distinct property sets, for example, for geometric uncertainty. There is also such an approach in existing 4x3 schema, and we are going to adopt this a little bit, but also extend it to describe other types of uncertainty that are not so much related to geometry, but more to the characteristics, and also uncertainty in a certain property, because there's a lot of existing mechanisms in IFC that we like to make use in these geotechnical models. And I think with this, we are at the end.
That's great.
Yes,
thank you. Thank you, Jonas. Thank you, Lars. You're pretty much spot on time, and thank you for that very interesting presentation. Thank you for taking us through those technical aspects of the IFC tunnel project.
Pleasure.
I think
I will stop sharing.
We're going to Jan Christian now, I believe.
Yes. My name is Jan Thorén, and I work at the Swedish Transport Authority in Sweden. So I will be presenting some of the domain expert work that we have been doing within the area of excavation, support, and tunnel lining. So you could say this is what comes after Jonas' presentation, after the geology and the rock data and the investigations. This comes when we start a project with taking out the rock and support the rock. So this presentation is mostly covering the requirements that we have identified within the domain team. So we will be talking about the actual domain aspects from here, and then Lars will cover it from the IFC perspective in the separate presentation afterwards. So generally, the excavation is there's a large variation of methods and systems and solutions around this, and but they share the same principle design. In the ground basis, it's a way of taking away the rock in different methods. There are different ways of supporting during excavation and after excavation, and there are different ways of waterproofing and building a final tunnel structure. And the methods and excavation and support depends on the actual site condition and tunnel design. As for instance, the rock mass quality and stability will determine how much needed to do support during the excavation and also afterwards. Water pressure and hydraulic sensitivity will decide on the waterproofing and the grouting and the sealing of the tunnel. And of course, tunnel section size, form, road, rail geometry will affect the tunnel design. The methods that we are covering in the report are conventional tunneling, mechanized tunneling, and cut and cover tunneling. You can see some of the examples that we have been based our report on. This is also different methods is also from different parts of the where the tradition is different in different parts of the rock domains, you can say, soft rock or hard rock scenarios. Different tunnel types and tunnel parts that we cover in the reports are, of course, different types of functionality of the tunnels. Parts of the tunnel that we see, it can be for the roads or for the rails. There are also different type of tunnel types. So we can see the ramps, or you have audits and portals and niches and cross passages and so on. We try to cover them all in the requirement report. Of course, different part of the tunnel is depending on how you do the blasting, and there's a lot of you can say terminology and different methods that we try to cover and talk about in the report. That will be in properties in the later stage. This is also connected to the space question and also connected to actual so to say details in the design. The support is also time dependent. It's usually for before you take out the rock or afterwards. You have temporary, permanent support. You also have phase stability and depending on the rock scenario. In the example, you can see there is not much of a pre-support. It's a hard rock scenario, but there are other scenarios where you actually do a lot of the support before we do the excavation. The principle is that phase stability and excavation stability for excavating the rock is usually done forwards in the face or above the face, like these spiling bolts that you see in the example. Where permanent support is usually done radially around the rock. Yeah, you see some more examples of that. Other things that included is injection grouting, dewatering drainage. We also have been talking about cast concrete or when you have all these type of different type of reinforcement or support that is been usually done when you have soft rock conditions. Here you see some example of shotcrete done in different layers, depending on the scenario, and you see also an example of an excavation in hard rock scenario or a soft soil scenario where you have much more pre-support and forepolling. There's some other pictures talking about the terminology from the theoretical, from an actual scenario where you combined it with bolts and anchors and lining in the scenario also. We have some more picture about lining. This can be done with precast elements. It can also be done in cast concrete. I have some more example later on this. A more example of precasted elements in one or two layers on different type of methods and different type of systems, you could say also. Even more on this scenario. And even more here. And all these different, you have joints and you have gaps and you have waterproofing and stuff like that. That is also components within in construction. Maybe not everything is actually model, but we need to be able to reference to some part of the geometry in this part. Here is an example of an in situ lining where we actually have the waterproofing. That's the yellow membrane you see there, and you have the reinforcement and the actual in situ casting. This is some examples of different type of excavation support and linings that we covered in the report of a requirements report. And now over to Lars to see how we model or worked with it from the report.
Okay, so there will be sort of about the same as the previous presentation, UML models, but now for the excavation support and lining subdomain then. And in a similar fashion as for geology and geotechnics, we have subdivided things into a couple of packages. One is the excavation taxonomy. We have ground improvement, pre-support, support, waterproofing, lining, and also some interior elements came from this domain group. So I guess this is again very, very small, but anyway, this is then the taxonomy from the domain team with different types of excavation elements like open slope excavation, brace slope excavation, anchored open excavation, and so on. And actually, I think I will then go to the next slide and just tell you what we did there. We from IFC 4.3 we have this element called IFC Earthworks Cut, and we had some discussions about that. And after those discussions, we actually decided to make a little bit of a split here. So we introduce a new abstract element, which we call IFC excavation, which then the existing IFC Earthworks Cut becomes a subclass of or a specialization of. So from a IFC file perspective, nothing actually happens with this if we don't introduce any extra attributes on this level. But then we actually we do that so we can add this IFC underground excavation element. So we have this split then between these sort of open excavations and the underground excavations. And while I'm on this slide, I should also mention that in IFC 4.3 we have an element which is called IFC reinforced soil. But while working with the excavation domain here for tunneling, we actually found that it would be nice if we could actually rename that element to ground improvement element instead, which is here, this with the brown border. So ground improvement is sort of a more generic term. So we actually propose we sort of take that definition and just rename it to also for example, include ground improvement when the ground is not soil, actually. And as you see here, we also introduce a ground reinforcement element, or we propose to introduce that as well. Yeah. So then we have earthworks cut here with all the existing predefined types, which are things like dredging and topsoil removal and trenching and pavement milling and so on. So, and we had a generic excavation predefined type. And what we propose to do is to actually add a few more special types of open excavations then, which are these braced open and anchored open excavation. And for underground excavation, we actually propose to introduce actually 2 predefined types to cover all of those that were mentioned here, like full face excavation, pilot bore reaming, profile widening, reprofiling, to actually introduce 2 predefined types. One is face excavation and one is radial excavation that covers sort of the sort of longitudinal or radial directions then. And then there was actually also a thing in the domain taxonomy which was called staged excavation, and we actually consider that as being something taking the temporal dimension into account, and we propose to use existing IFC mechanisms for that using the processes, for example. So that's that. And then
Lars, maybe we could talk about that we have not created element depending on the method of excavation. We don't have a TBM element, or we don't have a conventional tunneling element. We have said that the different methods for excavating is more of a property set. So that might be good to explain here, because the report and the requirement report is pretty much structure around the method of excavation, because that's we have made that decision to go with this instead.
Yeah, thank you. Please clarify any more if you feel I'm unclear.
No problem.
Yeah. So we go further into the ground improvement package, and here we actually then, as I said, we have actually proposed to rename this reinforced soil element to IFC ground improvement element instead. And by doing that, we can actually reuse many of the predefined types already defined, and we can add a few more predefined types to cover the requirements from this group. So both regarding dewatering, drainage, and also this ground freezing and deep soil mixing were sort of not already covered, while ground replacement or deep compaction and grouting and so on was already covered, as we saw with this reinforced soil element. So I can skip that. Pre-support, one thing I might mention here is that some of the elements we saw in the taxonomy, they sort of reoccur in different contexts. So what we actually propose to do is to introduce a couple of predefined types for IFC built system. Systems in IFC, for those who know that, is a kind of grouping mechanism where you can group elements into a system, and then the system sort of captures the functional aspect of sort of the functionality that this group of elements provide. So, for example, in this case, we have actually proposed to introduce a pre-support system in which you can then group all these different kind of elements that participate there. And for some elements, we can reuse existing IFC elements like plates, but we also added some new elements like the ground reinforcement element, where we have rock support bolts and spiling bolts, for example. And we also introduce a new predefined type for element assembly, which is this umbrella vault, which could be seen on the previous slides from Jan Christian. So yeah, so these are schema extensions then for this part, pre-support. And when we come to support, again, we propose to introduce another built system predefined type for this. And then regarding the individual elements, we had meshes and shotcrete and cast concrete. And discussions about these, because what we want to model primarily are the physical elements and the systems, and then materials in IFC, as you might know, is something sort of separate in the model. So, for example, for meshes, we have IFC reinforcing mesh already. We have elements that can be used for shotcrete, maybe like IFC covering, but we have also added actually an IFC arch element as a subtype of IFC built element. And there is already an arch type for IFC element assembly. So this new IFC arch would then serve as more like a unitary element. So you have the possibility to model then arches both as unitary elements and as assemblies. Further into support, we have things like anchors, which we then use again, these rock support bolts, predefined type, and any more sort of specific definition of what these things are, you can use classification or even your own user-defined property sets as well. We have annular gap filling. Here we actually added an IFC fill element as well as a subtype of IFC built element because there were also other needs for filling. So this fill element is basically an element that fills gaps between other elements. And then retention walls, we have already existing elements in IFC. And then we have lagging, which I have no picture of, but where we actually decided to add a predefined type for existing entity IFC plate. And then we also had yielding supports, and the result of the discussions here is we should actually add yielding properties to and have that possibility to many elements that can have this yielding capability. And even more support, and maybe not go into too much detail here. We have arches that we can use for support elements, and also we had some examples here of ceiling hose, for example, where we actually use IFC discrete accessory but add a predefined type, which we call structural ceiling. Otherwise, we can use, as you see, a lot of existing elements in IFC like piles and beams and so on. So again, a couple of schema extensions. I see I'm running out of time slightly. Schema extensions for IFC, for support, tunnel support. Not too much anyway in there. And lining was very small here. Again, we had a build system for also lining, where we can use arches either as unitary elements or as assemblies. And here we should also be able to use things like walls, slabs, columns, and so on, which are also existing elements in IFC. a separate package. We also add the waterproofing as a kind of build system. And here we can reuse, again, existing things like membranes in IFC. But we actually added 2 things, and I think I'm not the expert to be able to provide an explanation of this, but we have a water barrier which can sort of serve as a kind of barrier where you can compartmentalize the tunnel to sort of isolate water issues to compartments. So in this case, we actually added a water barrier type and also a type of spatial zone, which is this compartment, which is sort of very generic, but you could use it for then what is called cutoff in tunneling for waterproofing. Yeah. See, I have 1 minute left. We have also had an interior package from this group, and here we actually have a lot of elements where we can reuse what is already in IFC, things like partitioning walls and handrails and stairs and ladders and doors and manholes. All those things already exist in IFC. But we had one thing here, invert fill, which is then another predefined type for this new fill element that we added. And then we have things like ventilation, which will come later in the systems presentation. We have signaling also in the systems presentation, cabling, earthing, drainage also in systems. We had this duct bank, which appeared only here. And here we actually propose to add a duct bank predefined type to element assembly. And then last but not least, we have one thing that I also would like to explain. We have carriageway and track here to the right as sort of parts of the tunnel interior. And what is sort of worth mentioning here is that things like carriageways and tracks are actually part of the road and railway facilities. And the way IFC is done now in IFC 4.3, we sort of have separate facilities for tunnel, for bridge, for road, for railway, and for marine facilities. So the carriageway or track should then, in IFC terms, be also a separate facility that sort of travels through the tunnel. It's not the tunnel itself. So yeah, I think actually I should stop there, and so we can move on to the
could
next.
add a little bit about these tunnel types that will be. We talk about cross passages and access tunnels and other shafts and other types of tunnels. That will come later on in the definitions of spatial. Yes, you have it.
Yeah, so I have it here, but due to time restrictions, maybe we can mention that slightly tomorrow. We have, of course, added a tunnel facility with different tunnel types, and we also have facility parts the same way as we have done for road and railway and marine facilities. And we have also actually modeled the more lateral subdivision of the tunnel facility or tunnel parts as well. But I think there is no time to go into that now.
We will take that later on. Thank you.
Yeah.
That's a good call, Lars. Thank you. Thank you for that. Thank you, young Christian. I see we have Andre and Heiko with us.
Okay. Yeah, that should work. Hello, everyone. They're on the web and who are attending the summit and are interested in tunneling and BIM. And a happy welcome from me, Heiko Atzbacher. I would like to show you what our team, the domain expert group for systems, prepared on the topic of tunnel systems as a basis for the IFC tunnel standard and give you some information on the steps. First, I will give you an overview of the results of the working group. Then Lars will report about the implementation in the IFC schema. I present you briefly the following topics. Why do we need systems in tunnel? An idea of the scope. I show the main systems in the tunnel. I gave you an introduction in the spaces, and I give an example of the taxonomy for fans. To the scope. Tunnel systems are an essential part of tunnel construction since they might influence the conception of the entire system. Therefore, we need for these components of functional systems an exact description for the semantic and geometry to include them correct in the general model. In our work groups, we focused on those types of tunnels that are mostly spread across the world and are most interesting for the stakeholders. The same applies for the tunnel system to be considered. Together with the type of tunnels, mainly connected with its usage, the excavation method, construction type, geology, and geotechnical model, technical equipment plays a major role for tunnels since they ensure safe operation and maintenance. It should be observed that most of these systems are also required and used during the construction phase, even in a different or temporary capacity. Tunnels are highly equipped with a number of different technical systems. They are necessary for operating the tunnel, and some are already necessary in the construction phase. The considered subsystems are power supply, high voltage, middle voltage, low voltage, excluding the traction. It's mapped by the IFC railway, but with earthing, then SCADA or supervision, communication, ventilation, lighting, fire protection, passive and active, safety and evacuation, groundwater drainage or carriageway drainage. These subsystems listed here have been integrated into the existing IFC schema, and if necessary, this will be extended. Lars will report on this later. In this slide and in the following, there are some examples of typical tunnel systems that are considered in our analysis. It is important to observe that the systems are sometimes interconnected, means interfaces between several components, and quite complex. Each system is made of a series of components with their own characteristics and can be regrouped in subsystems for clarity purposes. Here is an example. A part of the subsystem safety shows signage and safety equipment, signaling, and various chambers. How we worked. We looked to get an agreement on elements and object types to develop a draft conceptual model and a draft schema extension. Important is to get property definitions and that are large complete, but will allow local variations. All should be amended in the IFC schema. For this, we defined the breakdown structure and the object type hierarchy. We named the spaces and the object. This picture we saw some more times today, but we defined spaces for excavation, support, lining, and spaces that host the system and the equipment. We defined the tunnel spaces, space reserved for tunnel components at the low-level detail, and standalone elements or actual physical elements in higher level of detail, and the relationship with each other. You see, some rooms can be placeholders for different applications or uses. In the work package 2, our work package, some work has been already conducted to create a tunnel taxonomy related to systems. So creation of the technical vocabulary used in the context of tunnel engineering, maintenance, and operation. For mapping the identified IFC entities has been started last year and goes to the end. Here you see an example for the ventilation. We structured the taxonomy to the IFC structure, looked for existing elements here, distribution flow element, defined the properties and attributes and the unit of measurement. Not all attributes are required for all van types. We have illustrated this for the IFC experts for the software implementation. We also looked for all components belonging to a van, like damper or sensors or air dust. I come to the end, to my end, and hand over to Lars with my finish. In the past, our office looked like this, a lot of folders and paperwork. I hope in future all our data information will be in the 3D model. Thanks for your attention.
Thanks, Heiko. That was great. I think Lars is back with us.
Yeah.
And I think you're going to share your slides. Here they come. Yeah.
Okay, I think you recognize these kinds of slides now, so I will bore you for a couple of minutes more with these. Good thing is that they look very similar, so if you understand one, you can understand them all, even though it might become a little bit boring during a presentation like this. So I'm now going to present the work we did with the conceptual model for the systems subdomain. And in a similar fashion as before, we have subdivided this into a couple of packages. We have a package for earthing elements, power supply elements, safety elements, ventilation elements, and then we actually have firefighting and drainage elements in one package. And then we have a separate package for systems. As I mentioned before, there is sort of a difference in IFC where you have system groupings, which are sort of elements of their own right, and you have then the individual elements that are grouped into these systems. And this is a nice mechanism where you can actually use a single physical elements actually in many system groupings. So actually a component can perform more than one function if you like. So actually first I just start then to look at the system structure in IFC. So we have, there are different kinds of systems. You have built systems and distribution systems. And here I show a structure for distribution systems where you have since before things like ventilation, electrical, drainage, lighting, earthing, power generation. And then I will come to this later. We have actually changed the definition, or we propose to change the definition slightly for fire protection, which is an existing type of distribution system. I will come to that. And we propose to add also a safety system. And you can read here the definition of what is a system in IFC and a note on how we look at systems. So we can continue from there. So if we then take a look at the earthing package, we can reuse the earthing distribution system to group elements that sort of contribute to this function. And in there we have things like connection bars, earthing conductors, earthing strips, grounding plates, grounding rods, fixed terminals, grounding meshes, and things like that. And for some, like conductors and connection bars, we have existing IFC entities already, cable segments more specifically, that we can use. But we didn't find, maybe people can help us, we didn't find a good basis for these earthing specific elements like earthing strips and grounding rods and so on. So we actually propose to add an IFC earthing element as a subtype of IFC flow terminal, where we can add then predefined types for these different types of earthing specific elements. So this is actually something that we propose for this part. Regarding firefighting and drainage, we have things like valves, where we already have valves in IFC covering the needs also for tunneling. And we have also things like fire hydrants and electrical tracing with things like cable segments and sensors. And also here we have pumps. We have already in IFC, and we have pipes in IFC, both pipe segments and pipe fittings, which we think that we can use to cover the needs also for tunneling. And then to the actual systems, when reading about fire protection on the web, we actually found that there was a distinction between active fire protection and passive fire protection. So active fire protection is about detecting, stopping, and escaping fire, and passive fire protection is about containing the fire and preventing it from spreading further. So what we actually propose here is to, because the current definition of fire protection system today talks only about a sprinkler system, which is of course part of a fire protection system, but we would like to broaden the definition for this kind of distribution system. So it's actually about this active fire protection, detecting, stopping, and escaping fire. So it could actually contain sprinklers and also sensors and whatever you need to achieve this active fire protection. But then we also propose to add, as a kind of built system, a fire protection type there as well, covering more this passive fire protection with walls and doors and things like that. So that's our proposal for firefighting and drainage. Regarding power supply, I think most is already covered by IFC. There are things in the domain taxonomy talking about, for example, low voltage cables and medium voltage cables and so on. And we found that this is in IFC, you have IFC cable segment, and you have no sort of knowledge on that level whether it's a low voltage or medium voltage. But then you have electrical systems in IFC, and connected to electrical systems, you have already defined property sets that defines the electrical system category, where you specify the high, medium, or low voltage. So in that case, we actually propose to use that existing mechanism to separate between these things. And then cable carriers, segments, and fittings are already existing in IFC, as are junction boxes. And if we go further, things like switches and circuit breakers and power generators and transformers are existing elements in IFC, as are switchboards, UPS, batteries, circuit breakers as well. So here we could just map it to existing elements in IFC. Let me check the time. And for power supply, we could use either electrical or even, if I go back, we had also power generation maybe could be used. But anyway, we propose to reuse existing definitions in IFC for this. Then we come into the safety package. We have things like doors, and doors are of course covered in IFC. there are things mentioned here specifically for doors, like lock systems and anti-panic system bars, like this wide thing that you can push to open a door. And there we actually propose to use property sets for going down to that level. But other than that, we have fans already covered. We have handrails already covered in IFC. And as I said, we propose to introduce this safety system as well. So you can group all the elements that sort of together provide the safety functionality. We have also lamps, and there are a lot of different types of lamps already in IFC. But here, things like lighting in case of evacuation or permanent lighting or arc, this is has to do with the shape of the lamp, actually, that it can be seen from all directions, I think was the definition of that. But in this case, we actually propose to again use existing or extend an existing property set. We have the lighting system in IFC, and there is an existing property set for lighting, so we could add properties to that to describe whether the lighting is just for evacuation or if it's permanent, as an example. More, we have things like tracking, and that is about tracking people and vehicles and things like that. And there in IFC 4.3, a monitoring system was invented. And right now this is defined from an environmental perspective, but we felt that monitoring system would fit this kind of tracking as well. We feel that tracking and monitoring are sort of synonymous. So we would actually like to use that, but that's maybe not decided yet. And yeah, we have some small things that we haven't dealt with, like sirens or sound beacons, whether we should actually add. And I think from the domain group, it was really important to know if a thing is a siren and not just a signal or a speaker. It should be something specific. So probably we need to add something for these specifically. Was not done yet. We have things like signage, which is already covered in IFC 4.3. IFC sign was already added there, so we propose to reuse that for signage, also for tunneling. And then we have things like waiting areas and airlocks, which we propose to put into the definition of a fire safety zone in IFC. And we still have this room for firefighters, kind of control center that we have not dealt with yet either. So will also have to be decided. And this becomes, I realize, very, very small for you. I can see it on my screen, but ventilation, we have things like sensors, but there we have IFC sensor, which has already a lot of types. And when looking at that together with the domain team, we saw that all the possible sensors needed were already covered. And then we have things like fans, air ducts, dampers, actuators, and sensors. And all of those actually also exist already in IFC. We discovered that we needed to add actually the jet fan as a new predefined type for IFC fan, but all the other types were already covered. And we have already IFC damper, IFC actuator, IFC sensor, and IFC duct segment, and so on. So a lot is already covered by IFC. as are also things like accessories, silencers, motors, things that were discussed here for fans in the domain group were also things like casing and impellers. And there we actually found that there are already property sets for fan that talks about impellers and things like that. So we actually feel that details about the casing or impeller could be handled by extending these property sets. But otherwise, we have already IFC electric motor and duct silencer and discrete accessory and IFC fan. So, and similarly for damper, we have accessories, we have actuators, and then we have blades and casing. And the same thing here, there are already property sets talking about blades. So we thought that blades and casing, again, could be handled by property sets connected to the damper. And this is actually the last slide now, just showing you also, we discuss not only the actual IFC model in GitHub that was mentioned, I think, by Andre, we also discuss all the issues regarding the conceptual model as well. So in the GitHub repository, in the issues list, we have issues that are labeled with IFC tunnel, and that is sort of everything that we have been or are discussing also regarding the conceptual model. So I just wanted to mention that. And I think I'm done there. And that was very quick, and there will be no exam now, but
yeah, we'll test people tomorrow after the second expert panel. Lars, thank you for that. I think that takes us through the whole of today's presentation. So I'd like to ask Michel and his colleagues to rejoin us on the screen. Please turn your cameras on. If I've taken you out of the stream, I'll add you back in. Yeah, excellent presentation. Thanks to you all for the update on IFC tunnel and the technical detail that you went into there. I know there's another session tomorrow, which is looking down my
10 a.m.
It's 10 a.m. isn't it? 10 a.m. Central
10
European
a.m.
time.
CEST, yes.
Yeah,
so that's GMT plus 2.
Which is expert panel 2. So we've got an opportunity to revisit any of the points that were raised today, and indeed go over several that weren't made. There are some questions and comments that have come in. I see Sergey has very helpfully been in and answered a number of them. But if we just bring one or two of them up for everybody's benefit, maybe not the best one to bring, but what Karen had to say.
I couldn't see the questions myself. I don't know whether the others did, but
yeah, they're in the comments box. If you click on comments on the right-hand side.
All right, okay. Thank you.
Karen Anderson, hi Karen. Karen was basically saying, have you checked the MVD's work being done for fire? There is a report regarding this. Yes, there's a occupants movement analysis report and also a fire safety engineering project that's starting up.
Absolutely. We got to know about this one recently. And I think there are probably a set of objects and concepts that we are bringing in that can be shared. Yeah, specifically on safety evacuation, we noticed that we were adding to the existing set.
Okay, that's good. I have access to that information as well, Michel. So you and I can talk on email, and I'll make sure you have access to the latest reports and other information that's available there. Ivandro from NGSIS has basically said, "Fantastic job, tunnel team. Lots of work in a short period. Can you spend a few words or thoughts on the envisioned software vendor testing, or is it too early?" And again, Sergey has provided this response, which is that it is a bit early.
I would add to that we have as well software vendors, members of our team since the very beginning. So we've been making sure they push us in the right direction in terms of easing the implementation that they'll have to do. So that was very important for us, and I can mention, for example, Sequent, but I should mention all of them actually. We did provide a great deal of help in optimizing the position that we've presented today.
Okay. And I can only support Sergey that definitely we will continue with more or less the same process that has been quite productive in both the infra room and the railway room with respect to the deployment project that we hopefully start in autumn. So that's the plan.
Thank you, Andre. Thank you, Michelle. And the other comments, again, Sergey has a response online, but Mileta, thank you, Mileta, says, do you have feedback from the many vendors about their plans and roadmaps for introducing fully BIM-based tunnel infrastructure design platforms in compliance with the latest BSI standards? Sergey replied to Mileta to say that that work is coming, I think.
Yes. The one thing I could add to this, because many of our stakeholders as well are, designers and general contractors, so they do BIM for tunnel projects on the geotechnical side, on the civil engineering side, on the system side, but they do so the difficult way, of course, because they are lacking this, this structured way of exchanging information that we will be bringing with 4.4, with IFC for tunnel. So no doubt, from my perspective, I think that software vendors will be very interesting to implement this, because this will simplify their work, the way they have to implement exchanges, import-export capabilities today.
Thank you. And there's one further comment that's coming from Vano. Thank you, Vano. He's asking about object types and observations. Why have observed object types their own objects? Observations as objects must be possible to link to any object. He goes on to say, and there are lots around observations in the PLCS standard to look at as interesting to implement.
For sure. Jonas, do you have an opinion on this? On top of your head?
Yes, Sergey answered to it in the chat. So he said,
okay,
maybe you want to say something, Sergey, but he mentioned that this is exactly the point, that we can attach this observation to any object.
Yeah, you're right. There's a series of answers from Sergey on that it's modular, so that it can be used on any object.
I guess it will be maybe some work later in an MVD phase, maybe to restrict this, but currently it's possible, the way it's modeled, to connect observations to any object using this very generic mechanism in IFC.
And I think from our side, it's important to mention that some of these observations live from the geometry they come along with. For example, if we have the outcrop of a certain material, or if we have the trace of a certain structure, of course, this needs to be an object with an own geometry where we attach the properties.
That's good. Thank you, gentlemen. Very comprehensive answer. We have no further comments or questions at this time, and we're 2 minutes over time, but I'd say that's pretty much running to time. Thank you for the excellent presentation that you've just provided, and the update and the expert panel number 1. Please join us again tomorrow morning, 10 a.m. Central European time, for expert panel number 2, also on the IFC tunnel project. And thank you, as I said, to all of our presenters. Very thorough and interesting and detailed, as always, on the project. and we're looking forwards to the output from the next phase of the project that will be coming later in 2022. Speak to you again tomorrow.
Thank you very much.
Thanks.
Thank you, everyone.
Bye.
See you. Goodbye.
Bye-bye.
Bye-bye.
Thank you.
Bye-bye.